All right, so I've talked to you about I've talked to you about the electrostatic force, and there's an equation. I've showed you that equation. I'm going to talk a little bit more about it in a minute, because we need to calculate it. But good news for you is I'm actually not going to require you to calculate it. We just need to talk about that equation. We need to talk about what goes into calculating the force. First thing you need to know is that there is a metric system or SI system unit for charge, and that unit is called the Coulomb or Coulomb. I think it's a French guy's name. Capital C is the abbreviation of that. 1 Coulomb is equal to 6.35 times 10 to the 18th electrons. That's a big number. That's a lot of electrons. You don't really need to know this, but there's something called an elementary charge. That's the charge of 1 electron, and that's a really small number, right? It's a charge of electron and a proton. The only difference is that proton is positive, electron is negative. Really, really small charge. So the point that you need to know about the Coulomb is basically this. 1 Coulomb is a really, really big unit of charge. One lightning bolt, the energy in a lightning bolt or the charge in a lightning bolt is about 10 coulombs. That's a not very big number, but the reason why it's only 10 coulombs is because 1 Coulomb is a ridiculously large unit of charge. Like if you get shocked with 1 Coulomb of charge, you're going to be hurting. 10 coulombs is like, bye-bye, see you next Thursday. So a Coulomb is a really big unit of charge. So let's talk about that force. You really need to know this. It's important to write this down. The force on two charged particles depends on two things. I'm going to move me out of the way. It depends on the amount of that charge, first of all, and number two, the distance between the charges. Amount of charge is Q, and the distance is D. You might want to write that down. And this equation brings that out. This equation shows it. It's the one that I just showed you a minute ago. Fe is the electrostatic force. Fe equals K times Q1 times Q2 divided by D squared. That's the equation. Now, good news, as I said earlier, you will not have to actually do calculations with this equation, but I want you to know it, and I want you to know what it says about these two things, about the charge and the distance and how they affect the force, right? So like I said, Fe is force. K is that constant I was talking about in the last video. K is the electrostatic force constant, 9 times 10 to the ninth. It's a humongous number. You don't have to memorize it. It's actually in the chart. Q is charge, and we're talking about the force between two charges. So we have a Q1 and a Q2. Notice these are not superscripts, they're subscripts. So it's not a squared or anything like that. They're just to separate and Q1 from the first charge from the second charge. And then distance, this is a superscript. Distance is squared in the equation. So we need to talk about this equation. In order to understand it, we need to go back and review something that I know I've talked about in my class, but especially for my connected learners, you might not know this yet. And so we need to talk about just in general, in any equation and anything we're talking about, the relationships between variables. This is a really important thing to know. So basically, there are two kinds of relationships among variables or between variables. You can have a direct relationship, or you can have an inverse relationship. Now pay attention, write those down, and I'm going to explain to you what those two things mean. All we need to do is look at any equation, and we can easily tell what the relationships between two variables are if those variables are on opposite sides of an equation. If two variables are on opposite sides of an equation, it's easy to determine their relationship. I can see it real easy. So for instance, here's an equation. Imagine A equals B over C. We've had lots of equations already in this format. Now, one thing we need to remember is that even though there's a whole number over here on this side, remember there's an understood 1 under this. So this is basically a fraction equal to a fraction, but the point is this makes it a little bit easier for us to understand these relationships. Obviously, this equation doesn't really look like this. It looks like this. But the point is to remember that because we know there's an understood 1 under here, that A is actually in the numerator. And that's important because if I look at, for instance, the relationship between A and B, I want to know what that relationship is between those two variables. They are both on the top of their fraction bars. If two variables are both on the same side of a fraction bar, either both on the top or both on the bottom, they share a direct relationship. We say that's a direct relationship. And what you need to know about a direct relationship is that one causes a change in the other. Specifically, if B increases, A does the same thing. That's what a direct relationship is. B goes up, A also goes up. Vice versa, if B decreases, A decreases as well. So a direct relationship means it causes a change in the other variable in the same direction. That's a direct relationship. As an example, if we plug in some numbers here for B and C, let's say B is 20, C is 5, 20 divided by 5 is 4. Let's now just increase B. Let's change 20 to 40. All we do is increase B. 40 divided by 5 is 8. Notice that if B increases, so does A, so does the answer. That's what we just said. It's a direct relationship. Now let's go back to the inverse. If we look at C and A, C is on the bottom, A is on the top. That's opposite sides of the fraction bar, so that's called an inverse relationship. Inverse relationships, they don't change in the same direction, they cause changes in the opposite direction. So that means if C increases, if the value of C increases, that will cause a decrease in A. C goes up, A goes down. Vice versa, if C goes down, A will go up. It's an opposite change. That's what an inverse relationship is. As an example of that, we'll put the same numbers in. We started with the same one before, 20 divided by 5 equals 4. Now I'm going to change C, and I'm going to increase C. Instead of 5, I'm going to make it 10. C went up, and we see that A actually went down. A was 4, and it went to 2. This is an inverse relationship. If C increases, A will decrease. That's the nature of an inverse relationship. So let's apply this to our electrostatic force equation. Here was the equation, and again, we need to remember that there's an understood 1 under here. That means, just so that we know, this force is actually on the top of the fraction bar. It's in the numerator. So we said earlier that the electrostatic force depends on two things, or is related to two things. It's related to the charge, and it's related to the distance. Related to Q, actually the product of the Q's, and it's related to the distance. So we start out with charge. Charge and force are both on the top of the fraction bar. Since they're both on the top, they share a direct relationship. Direct relationship means as charge increases, the force increases, and vice versa. Charge decreases, force decreases. In practical terms, that simply means the greater the charge, the greater the force, smaller the charge, the smaller the force. So you need to know that. Distance is the other one, but distance is in the denominator, force is in the numerator. Hopefully you know already that those are inversely related. They share an inverse relationship, which means if D goes up, force will go down, which means, practically speaking, when charges are farther apart, that means their D is increasing. If D goes up or increases, forces go down. So the charges that are farther apart actually exert weaker forces on each other, but when charges are closer together, they exert stronger forces on each other. So you need to know this. This is a really important slide, that distance and force are inversely related, and you need to know what that means, and charge and force is directly related. You need to know what that means. So to make sure that you understand this, look at these and see if you can figure out what word goes under this red box. Pause the video real quick and see if you can figure that out. So you should know that the closer the charges are, the stronger the force. That's because closer, that's about distance. Distance goes up, force decreases, but in this case, the distance is going down because charges are getting closer. Distance goes down, force goes up. That's an inverse relationship. The larger the charges are, hopefully you know that the stronger the force is. Charge goes up, force goes up. That's a direct relationship. Just a few final points now that we need to talk about the electrostatic force. Just a few more things you need to know. Again, you don't have to calculate this force. I'm not going to make you do that. But you do need to know that just like any other force, all forces are vectors, which means they have both magnitude and direction. Before this, we talked about forces using directions like left, right, up, down, positive, negative. We're not going to do that with electrostatic force. With electrostatic force, there's only two directions. The direction is either attractive or it's repulsive. Because remember, opposite charges attract, like charges repel. Those are the only two directions that we really need to talk about. The other last thing that you need to know about electrostatic force is that, you might have guessed this, the electrostatic force is a Newton's third law pair. Remember we talked about Newton's third law a long time ago? It's about equal and opposite forces. Well, the force between two particles is actually a force that they are exerting on each other, and it's always equal in magnitude, but it's opposite in direction. So if you look at these pictures, for instance, here, we have charge number 1 and charge number 2. This arrow represents the force of number 2 on charge number 1. It's attracting it. Same way on the other side, this arrow represents the force of charge 1 on charge 2. They're both attracting each other, and these forces have exactly the same magnitude. It's a Newton's third law pair. Same thing down here, but it's a repulsive force. They're both negative charges, so they repel each other. This is the force of charge 2 on charge 1. This is the force of charge 1 on charge 2. They are repelling each other with equal magnitude forces, but in opposite directions.